Thank you very much for inviting me. It's always been a real pleasure to come here to MUG. This year especially, there's something which my group is very excited about. It's really a completely different way of doing checkpointing, in my opinion. So what I'll do is in the first 10 minutes or so, I'll try to give you a quick review of what our traditional software was and what is the path that led us toward doing checkpointing now in a completely different way. So the first 10 minutes is going to be a very fast run through of what we've done. So if you wanted to hear it in detail, you should have been here during the last 5 years listening to each of the talks. On the other hand, I think that our new way of doing it is sufficiently different that for those of you who have been here the last 5 years, please ignore whatever I said the last 5 years, because I think now we know the right way to do it finally. So let's get started. So let's see. So we're going to first a quick review, then we'll talk about the idea of plugins. Plugins are very basic to our own checkpointing approach. And at that point, we'll go on to the idea of proxies. Proxies were halfway toward the new approach that we have for checkpointing now. Finally, we'll get to split processes. Split processes, so number 4 in that outline, split processes is really the core of the new idea. And this is what has us very excited about what can be done in the future after this. Okay, so just a bit of history. We've been around for almost 15 years now. There are a series of publications, more than 100 refereed publications, talking about how other groups use our DMCCP software for checkpointing. And it's very easy to use. Here you see DMCCP. Let's see if I remember how to do this. Yeah. Here you see DMCCP launch, and then you give the normal command line. When you're ready, you give the checkpoint command, and then it will dump out these DMCCP files, and then you can do a restart. And the idea of the way we do it is we want to do it completely in user space. We don't make any modification to the kernel. We don't modify the executable. So when we say transparent, we mean completely transparent, completely non-invasive. No root privilege needed. You just take it out of the box and start up and run. And then this means also that when we apply it to MPI, in some sense, we aren't really aware of which MPI we're running to. For us, it just looks like some weird distributed computation with a lot of processes on different hosts. So it just works. So the DMCCP, the D there stands for distributed. So therefore, automatically it applies to almost any MPI. I won't say very much about the internals, but I'll just say that we have a centralized DMCCP coordinator. That could easily be replaced by a broadcast tree if we were worried about a single point of failure. And then we start up a process. We insert our own checkpoint thread in each process. And then when it's time to checkpoint, we get a checkpoint message. Here we can see the checkpoint message. Comes down to the checkpoint thread. It tells each user thread to pause. That message will go to everybody in that computation. We then have to drain any data in the socket, or if that's InfiniBand, we'll have to drain it out of the InfiniBand switch. We have a way to do that I won't describe here. And then we can individually save each process as a memory image and then restore it. And naturally, we keep track of things like open files and so on. Okay, so the question that's been keeping us interested for 15 years is this question in green. What are the limits of checkpointing applications in the real world? So in the past, HPC meant you have your computation running in an isolated world. It doesn't talk to anybody else. There is no external large database. There is no server that it has to download data from. It just runs by itself. that world is on its way out. So now we want to know, can we keep up? For example, one of the very simplest things is these CPU accelerators are becoming more common, such as GPUs. How can you checkpoint GPUs? And as we'll see, if you want to do transparent checkpointing of GPUs, at this point we're sort of the only game in town in terms of doing it practically. But in any case, that's what's been driving us. It is scalable. So there's a paper here that demonstrates how to, that has demonstrated running with, in one case, 32,000 CPU cores, in the other case, 16,000 CPU cores. These are real world or close to real world benchmarks that are commonly used. Good. Now, to make that work, we have this idea of plugins. So plugin, of course, is a common word. And why plugins? It's precisely because of what I said. Processes must talk with the rest of the world. So we call this process virtualization, this idea. And maybe the best way to explain it is by a really small example. If you have several friends, each of whom has their own way of doing checkpointing, and you want to ask just one question to figure out what's the difference between what your friends are doing, the one question should be, how do you handle a process ID on restart? Because prior to checkpoint, the kernel gave you one process ID. On restart, it will probably try to give you another process ID. I won't go into the other approaches, but for us, what we do is we allow the kernel to give it any process ID we want, because we want to operate in user space transparently above the kernel. And then we're going to keep this table down here, this translation table. And whatever the kernel says our process ID is, we'll lie. We'll give it our favorite process ID. So this process thinks he's process ID 4000. This one thinks that she's 4001. And the way we do this is we'll interpose on any system calls, at least any system call that refers to a process ID. So whenever we see a process ID coming from the kernel, if it's a new one, we give it a new virtual PID. If it's an old one, we look it up. And then similarly in the opposite direction. Then on restart, everything is very easy, because on restart, we can restore this memory image, and these user processes continue to think they are process ID 4000 and 4001. They thought that was always their process ID. Nothing has ever changed. But internally, we will still interpose on system calls, and we'll look up this process, what's the current process ID? This process, what's their current process ID? We update the table, and after we update the table, we're in business. But this is a really core idea that can be applied across many areas. You can do that for network addresses. You can do it for path names. If you move from one batch slot to another batch slot, and now the prefix of every path has changed, no problem. We'll just interpose on any system call that knows about path names. If it's InfiniBand, we have a certain way of handling the structs in InfiniBand, and so on. So a lot of our research for a while was, can we invent newer and better plugins that will expand the world that we can play in to InfiniBand, maybe to the GPUs, but it turned out GPUs were harder. So it's at the point of GPUs that we had to change to a different approach. And that was the beginning of this path that we're on right now. We'll still use plugins, but plugins are just one tool. And it's no longer the primary tool. OK, first, just to say a little more about why we think about our checkpointing is actually very widely used, not just in HPC. Here's a really interesting example where it's used, in fact, by Intel. Intel, Mentor Graphics both have co-authored papers with us. So this is for electronic design automation. Again, I won't stop to say too much here, but I'll just say that when a company like Intel might be designing a new CPU, if they have a software simulation, that might run 1,000,000 times slower than silicon. So they will use a hardware emulator. With a hardware emulator on the back end, now it only runs 1,000 times slower than true silicon. Well, that's great. If it only runs 1,000 times slower, then if they wanted to, they could boot up Microsoft Windows overnight. And then they could proceed to test on Excel and Word and whatever. But of course, what they would really want to do is boot up Microsoft Windows once, checkpoint, and then restart from there. Or maybe boot up Windows, start up Word, and then checkpoint and go through each of the menus one by one. So this is now possible because we have designed a plugin, and now there's a three-way cooperation between Intel and the vendor of a hardware emulator and us. The Intel software, of course, is highly proprietary. They will not share it with the vendor or with us. The vendor of the emulator, their work is also proprietary. They're not going to share it with us. And we have this open source software in the middle. So what's going on is, with the encouragement of Intel, the vendor of the emulator develops a plugin that runs on top of our DMCCP checkpointing. And then their plugin allows their machine to play nicely with us. And actually, this turns out to be a very small request, because an emulator of this type, it's usually expensive, and it might have 1 million lines of code, and it has a lot of very complex hardware. So even internally, any rational company is going to have a command to dump the state of the machine, and then later to reload the state of the machine, just for their own internal debugging. And so all we're asking is, please put a wrapper around that as a DMCCP plugin. And then when it's time to checkpoint, that plugin wrapper will dump the state of the machine, and then it will reload the state of this hardware emulator at the time of restart. OK, so now I think you have an idea of the ecosystem in which we play. Now that the ecosystem is clear, let's see where we can go from here in what I think is a very different direction from what historically has been the path of checkpointing. So initially, our idea was proxies. And of course, other groups have used proxies too. So again, I'll go through this a little quickly. But coming back to our fundamental question, we want to know, what are the limits of checkpointing? And for a while, up until about CUDA version 2, there were some other groups that were able to do checkpointing, for example, at Riken, Japan. But then it stopped working for certain technical reasons I could talk about. But ultimately, what happened, in my opinion, is when NVIDIA wanted to support unified virtual memory, or just unified memory in general, a single address space across the GPU and the host both, they had to change their library so it could no longer be closed and reloaded. And suddenly those other approaches to checkpointing started failing. So in any case, we needed a method that did not rely on closing out the CUDA library and then reopening it at restart time. And so this caused us to realize, well, why don't we just start a completely new CUDA as a proxy process? And then if we ever need anything from CUDA, we'll just pass the request to this second helper process, and they can do the work for us. And now now at the time of restart, we will generate a new helper process, a completely new CUDA program, and we no longer have this problem of having to close a library and reopen it. So this is roughly where we were as of about a year and a half ago. So initially, we might have an application, talks to CUDA library, which talks to the GPU. We added, I still forgot to reverse these. We have a proxy process in the middle here, and here is our application on the far right. And that application will send a request for a CUDA command over to the proxy. The proxy will then send it over to the GPU. And why is this better? Because when it's time to checkpoint, we will only checkpoint the application process here. We will not checkpoint the proxy process. And then at the time of restart, we will start a new proxy process. It will advertise itself to the application, and the application continues where it left off. So this works. There are some details there, but it works. Unfortunately, the overhead in some real-world applications was about 6%. So it told us we were on the path to something interesting, but maybe there was still more work to do to make this completely practical. But at least we can do the transparent checkpointing. The world had lost that after CUDA version 2. By CUDA version 4, the world had lost transparent checkpointing for GPUs. At least we brought it back again. Okay, so any case, that work was called CRUM, and crucially important, we do support the unified virtual memory. Recall that with CUDA version 4, that's when NVIDIA broke the old checkpointing schemes by saying now you can use unified virtual memory. And the world really wants unified virtual memory. It's analogous to the virtual memory in ordinary Linux. Yes, you could always do your own overlays. You don't need virtual memory in Linux. But if you program without virtual memory, life was very painful. And there's a similar story for NVIDIA and CUDA also. Unified virtual memory makes life a lot more pleasant. So we support it all without restriction. And here are the 6% overheads. But let's reserve some time to talk about what's really new now. So here we're calling this split processes. And the name of our software is called MANA. And here you can see the title, MANA, MPI agnostic, network agnostic, transparent checkpointing. So what do we mean by agnostic? What we mean is that we are going to checkpoint an MPI application, and we don't really care which MPI it is. And when we restart, we don't care if we're going to restart under the same MPI or a different MPI. And even better, we don't even care if we start under the same network. Could be a different network. Whatever MPI we restart with, that MPI can choose their favorite network. We don't care. It means we could even migrate to a different cluster, which has a different favorite network. So we could easily understand that if we think about proxies. In the case of proxies, it's quite obvious that we can change the internals of that proxy process, and the application process shouldn't care. But now we want to do this with a single process. So remember the 6% overhead we had for NVIDIA CUDA? The reason there is we tried every trick we could think of. We shared memory, cross-memory attach. There were several interesting talks and in the tutorials yesterday where they talked about how MPI also uses these ideas to have a much more efficient communication between hosts, between MPI ranks on the same host. But our thought was, let's see if we can put the, I'll continue to call it for a proxy program for a while, but let's put the proxy program and the application program into a single address space as a single process with even a single thread of control. And that single thread of control will just switch back and forth between these two programs. So we call these two programs, we refer to them as an upper half program and a lower half program. And we will try to internally tag all of memory so that we know for each memory region, either it's part of that upper half application program or the lower half program for driving MPI and the network. And then we're going to play something very much like the old game, where at the time of checkpoint, we'll get rid of the proxy in the middle, and then at the time of restart, we'll choose a new favorite proxy. Could be different. But this time, we'll be choosing a new lower half program. OK, so what does this give us? Well, as it says, we can load two independent programs into a single process, and they'll be sharing a single address space. And I'll just briefly comment, there's a different approach, which is maybe interesting intellectually, process in process. There they were targeting MPI itself. In our case, we're targeting checkpointing. And one of the authors there, in fact, is an alumnus, I think is the singular, of MPICH. So Next, we finally have that low overhead. We're getting rid of that 6% overhead because we don't need to do cross-memory attach or shared memory. It's a single process. Single process, 2 programs, but now we have this magic feature that the application program can pass a pointer down into the MPI program. And the MPI program sees all of the address space, including the address space of that upper half program which runs the application. So now we are no longer hiding each program from the other one. We've gotten rid of that isolation. Normally in Unix or Linux, isolation is a good thing. But here it's a bad thing. And so we're working a little harder to get rid of that isolation. We also guarantee there will be no address conflicts. So we run one in upper half memory, another in lower half memory. And that's part of what made this somewhat difficult. But in any case, now finally the MPI and the network libraries are isolated in a separate program. And so when we do a restart, we've now broken that problem into 2 independent problems. Problem 1, start up a new MPI and network. Your favorite choice, we don't care which. Problem number 2, restore the application memory. And then when you're done, let them communicate with each other again. Basically reconnect the plumbing between those 2 programs. Okay, so, whoops, wrong direction. Oh yeah, and so what we can do is we can dynamically change the configuration of the MPI. You no longer have to set on the command line the parameters when you launch an MPI application. You can even switch, let's see, yeah, there we go. You can even switch from one MPI to a totally different one, or even a different network. InfiniBand, you can move over to Cray GNI if you like. And you can even migrate to a new cluster with a different number of CPU cores. And in each case, there's the question, why not? After all, these are independent programs. They have nothing to do with each other. Why should one program care what the other program is doing? It's only in the plumbing between them that we allow the application to make a call to the MPI program that can satisfy your MPI requests. Okay, so it means we can solve problems like this. And here we have an example where we've changed everything, the number of cores, the MPI, even the network. So, and we can do this even for cross-cluster migration, and it will be efficient. That's the other thing. Because when we go to a destination cluster, obviously we're going to choose a native MPI of that cluster that has been carefully tuned to run the best on that cluster. Okay, and we will respect transparency. That's been our target from the very beginning of this DMCCP project. So nothing gets recompiled, nothing gets relinked, and it just works. And as we said, it's agnostic. We don't really care what Linux, what MPI, what network, because that's part of a different program. The application is just communicating with that independent program. It also satisfies another problem. Transparent checkpointing for MPI is a bit painful. Partly it's because we have this m times n problem for maintenance that I like to talk about. So here we have a number of different MPIs. Here we have a number of different interconnects or networks. And if we want to really maintain each of them and have some knowledge of what's going on, it becomes a little complicated. But if we don't care, because now we're going to put all of this into a separate lower half program unrelated to what we're doing. And then we'll just make sure to connect with the proper plumbing. And again, we'll maintain that single address space. We want that single address space because when we pass a request to make an MPI call, we want to pass a simple pointer to our buffer in the upper half. We do not want to copy the upper half buffer into the lower half. We'll just pass a pointer. So independent programs, but the address spaces are no longer hidden from each other. They can each see the address space of the other. And we make sure that there will be no address conflicts. Okay, so here we go. MPI agnostic, network agnostic. Again, I won't stop to go in all the details, but basically, when it's time to, a lot of this I think I'll just leave up here, and you can view it in detail, and then if you're really interested, maybe even read the paper, which has the full details. Instead, I'm just going to concentrate on the high points here. And this is one of the high points that I'm going to come back to. So this is the problem of collective communication. So it seems like this is a very nice and elegant way of doing things, but it turns out that for collective communication, it will be more difficult, because that's when we have an all-to-all communication problem in the lower half, which must somehow respect the plumbing in the upper half. Suppose some of the upper half processes were in the middle of a collective call and other processes were not, maybe because they're still doing their task and they haven't reached that point. So we'll come back to that point later. But in any case, now when it's time to checkpoint, here's our new picture. Here we have the upper and lower half. Good. And here we're calling it by exactly that. By the way, upper and lower half, that's in analogy with the idea in device drivers in any operating system kernel. In a device driver, people will frequently refer to a lower half that talks closely with the driver that works with the physical device, and the upper half is talking with the application process and getting requests. So there also they have this idea of isolating an upper and lower half. So that's what we're going to do. So at this point, when it's time to checkpoint, here's the only permanent data that gets saved. There's nothing down here to be saved, because we're going to replace it with our favorite MPI later. So drain the network. We'll checkpoint only the upper half. And then when it's time to restart, for convenience, we'll start with the lower half. We'll restart it. So what are we doing here? We've perhaps moved to a new cluster. We're taking our favorite MPI there. And we're just starting the MPI across the number of nodes that this application needs. And right now, it's the trivial MPI application. It knows nothing at all about what the world looked like prior to checkpoint. This is just a fresh new MPI whose only job is to run the trivial MPI and to advertise the address of every MPI call, just in case the upper half wants to make an MPI call. So the only thing we're doing is we're going to advertise the addresses of every MPI call so that it will be easy to connect the plumbing later. But that's all. OK. Now, so we'll reinitialize the MPI. If there was any, we'll reinitialize the MPI. And then at this point, each lower half knows what is its own MPI rank. It'll go looking for a checkpoint image file that corresponds to the same MPI rank. When it finds the matching image file of the same MPI rank, it can then load the upper half. And now these ranks will match up perfectly. And now they match up perfectly. During restart, we'll spend a little time in further initialization, because maybe prior to checkpoint, maybe the application had created some derived data types. Maybe they had a specialized topology that they declared. But luckily, with our idea about plugins, we had noticed when they changed the topology. We had noticed when they created derived data types. So this is the point at restart time that we're ready to now create the same derived data types, or to recreate the same topology, the same core affinity, whatever it is that we need in order to make this semantically equivalent to what used to exist. OK, and so then here's the answer. Now we know how to checkpoint under one system and then restart under another that looks totally different. And basically, it works. So here are measured overheads. So we're seeing 0.6% and 0% for two well-known applications. The checkpoint time is very reasonable, so on. Furthermore, we can now checkpoint and restart between clusters. And then finally, I'll stop very soon, but this is, if you remember, I advertised that there's more to say about collective communication. This was the one puzzle that took us quite a while before we could finally be satisfied this is going to work. So what's the problem with collective communication? Why is that so hard? Well, the idea is when it's time to checkpoint, since this is transparent checkpointing, we wish to checkpoint whenever. The coordinator will simply announce time to checkpoint. It's like a game of musical chairs. The music stops, everybody has to sit down. It doesn't matter what they were doing at that moment. Okay, so we have two cases. Maybe we were in the middle of the collective communication, or maybe we haven't even begun. And it would be nice if only we could recognize these two situations. But it's really hard to do that, because then we would need to be sitting above the entire computation, knowing what every single process is doing. That could be done with a lot of instrumentation. It would threaten to provide greater overhead, and there are other reasons why I would be worried. So ultimately, what we did is we introduced an extra trivial barrier in front of every collective communication. And now recall that we have our plugins. So if anybody ever makes a collective communication call, we will insert a call to MPI barrier, just the regular MPI barrier, and then the actual collective communication call. Why is this helpful? Why does this simplify the problem? And notice the trivial barrier hopefully is very fast compared to the actual collective communication. So this simplifies the problem because, let's again go back to those two cases. But now we can say maybe some processes are still in the trivial barrier. Well, if some processes are still in the trivial barrier, by definition, no one can begin the next collective communication. You cannot begin a new barrier until all the processes are ready. And it's not true that all the processes are ready. Some are still inside the trivial barrier. So if some processes are still inside the trivial barrier, that gives us the guarantee that no one is inside the collective communication, no one at all. And now we'll just kill the lower half, and then on restart, we'll tell them begin the trivial barrier one more time. No harm done. It's a completely different MPI. The new MPI never even knew that the old MPI was in the middle of a trivial barrier. So no problem. Okay, but maybe we're in the other case. Maybe some processes are still in the actual collective communication. But now, if some processes are in that collective communication, that means that no one is inside the trivial barrier. And furthermore, no one it means that every process has actually begun the collective communication. All processes are present and computing. If all processes are present and computing, okay, let's wait another minute or two until the collective communication finishes. So in the first case, maybe one process is still working on a task. It's going to take another hour to finish that task. We don't want to delay the checkpointing for 1 hour. We want to checkpoint now. Can we recognize that? In the second case, everybody has begun the collective communication. So it's good to know that. And now so let's just wait until the collective communication finishes. So by adding these trivial barriers, we can recognize those two cases and handle each of them efficiently with very little overhead or instrumentation. And so that pretty much tells the story. Thank you.